Hello, everyone. It's a pleasure to have Annika Heckel as a speaker today. We'll talk on non-concentration of the chromatic number. As usual, if you have questions during the talk, please write it in the chat. Otherwise, there will be plenty of time at the end of the talk to ask questions. And we will also have some informative session, which will not be recorded if you have further questions, which you don't want to be recorded. Okay, Annika.
Right. Yeah, hello everyone. Thank you, Liana, for the introduction, and thank you for the invitation to speak here. Yeah, so this talk is about colorings of random graphs. So I'll start by reminding you what a coloring is. Of course, most of you will be familiar with that. So the setup is we have a graph, and we want to give a color to each vertex, and we want to do it in such a way that neighbors always get different colors. So this is an example of such a coloring. So you can see this vertex and this vertex are neighbors, and they have different colors. Now we want to know how many colors we need to do this. So the minimum number of colors where this is possible is called the chromatic number. And we denote this by chi of g. Now, as I mentioned, we want to look at the chromatic number of a random graph. So we're just taking the standard random graph GMP, where we have n vertices and include every edge with probability p independently. Yeah, so what can we say about the chromatic number of GMP? So of course, the chromatic number of GMP is a random variable because the graph is generated randomly. So there are kind of two main directions of research concerning the chromatic number of GMP. So first, maybe the most natural question when thinking about the chromatic number of GMP is, well, what is it? What is its value? Can we give any upper and lower bounds? Now, as I said, the chromatic number is of course a random variable, and in principle, it can be anywhere between 1 and n. So any bounds that we give always hold with high probability, with probability tending to 1. Now, the other main direction of research has been, okay, even if we can't pin down the exact value of the chromatic number, can we say anything about how much it varies? So if we generate GMP, we sample GMP, say 100 times, and 100 times we work out the chromatic number, how close together are the results going to be? So in other words, what's the length of the shortest interval so that the chromatic number of GMP falls inside that interval with probability tending to 1? Okay, so let me first say a little bit about this first question, about the value. Now I say GMP, but actually for most of this talk, P is going to be 1/2. So we're looking at the dense random graph GN 1/2. And this is also, so GN 1/2 is also what the random graph that most of the early results on the chromatic number of GMP were about. So Gromit and McDermott started studying this question in the 70s, and they worked out the order of magnitude of the chromatic number of GN 1/2, and it's n over log n. And then it remained an open question for quite some time what the asymptotic value of the chromatic number of GN 1/2 is, until it was settled in a well-known paper by Bollobás from '87. So he showed asymptotically the chromatic number of GN 1/2 is given by this expression with high probability. So this was already known as a lower bound, and the lower bound is easy, and the tricky part is showing that this is an upper bound. Okay, this result was sharpened a couple of times by all of these people who gave either sharper upper or lower bounds. Now the best bounds that we currently have, the best information that we currently have about the value of the chromatic number of GN 1/2 is given by this, this result from 2016. So we have an expression here that is an estimate for the chromatic number, and we know it holds up to accuracy little o of n over log n squared, with high probability again. Okay, so this is what we know about the value of the chromatic number. Now, how about concentration? What's the shortest interval? What's the shortest interval length that we might give that the chromatic number is contained in with high probability? Now, this formula here, of course, automatically gives us some sort of concentration result. It gives us an explicit interval of length little o n over log n squared, which contains the chromatic number. But this is not a particularly short interval. And it turns out, if you don't actually have to specify which interval you're talking about, you can do a lot better than this. So the starting point for these kinds of questions is a well-known result by Shamir and Spencer, also from '87. So they proved that for any p, and in fact any function p of n, the chromatic number of GMP is always contained with high probability in some sequence of intervals of length about root of n. Okay, and this result actually doesn't tell you anything whatsoever about what the sequence of intervals is. But we know it exists. Yeah, it's a very general result because it holds for any function p. So this is shown using martingale inequalities, martingale concentration inequalities. And nowadays, this is a completely kind of standard argument in random graph theory using the vertex exposure martingale. But this theorem is actually the first instance where that was used on random graphs. So they kind of found this tool and then applied it to study the chromatic number. Okay, so this is a very general result. And in this generality, it can't be improved. So it's not hard to see that if you let p tend to 1 relatively quickly, the chromatic number of GMP actually is spreads out on an interval of length root of n. It's not hard to show. It basically comes from non-concentration of the number of edges for this random graph. But for special cases, you can improve it considerably. So first, for our favorite random graph gn1/2, well, you can improve it slightly to root n over log n. So you can get another log factor out. So this is given as an exercise in the book, The Probabilistic Method. Okay, but if p tends to 0 reasonably quickly, so if p is less than n to the -1/2 minus epsilon, you can improve this quite dramatically. So in this case, the chromatic number of GMP is actually 2-point concentrated. So there are 2 consecutive values, and we know that the chromatic number of GMP takes one of these 2 consecutive values with high probability. So this was shown by Alon and Krivelevich in '97. Now, none of these things actually give you any information whatsoever on what these intervals are and what these 2 values are. So in some cases, we actually know what the values are. So Achliaptas and Noah gave 2 explicit values for p a constant over n. And this was extended to 3 explicit values for p up to n to the -3/4 some years later by Koya, Okler, and Panayiotou and Steger. Yeah, so this is what we know basically about concentrations. So we have a very general result, root of n, which can only be improved slightly for gn1/2. But if the random graph is sparse, we have very, very sharp concentration. What we didn't have until very recently was any sort of non-trivial case where we knew 2-point concentration doesn't hold. Erdős raised this question in I think I've been told he raised it in the late 80s, but the first reference I could find was from 92. And he asked specifically about the dense random graph G(n)1/2 and whether we can show that the chromatic number of G(n)1/2 is not concentrated on a constant number of values. So if you recall the upper bound that we have, the best upper bound is root n over log n. So that's quite far away from that. But even that, yeah, we couldn't show. Yeah, and as I said, there are some trivial cases where the chromatic number of G and P is known not to be concentrated. Bollobás in 2004, he wrote a paper where he kind of reiterated this question and asked for any non-trivial examples of non-concentration. And again, he raised G(n)1/2 and asked whether we can show that the chromatic number of this random graph is not concentrated on 100 integers. Okay, so the result I want to talk about for most of the rest of the talk is the following. So we're going to show that the chromatic number of G(n)1/2 is not contained with high probability in any sequence of intervals of length n to the 1/2 minus epsilon for any fixed epsilon.
Sorry,
yes?
Annika, there is a question whether there is an easy argument why you couldn't have concentration even on one point.
On one point, well, for which graph? For G(n)1/2?
Or for whatever. So, you know, there are these 2-point concentration results. So whether they are.
I guess you can't do better because for some continuity reasons, as you increase P and the chromatic number, at some point it would jump to the next integer. So somewhere in between, it would be, weight would be on 2 consecutive points.
Mm-hmm.
So as you increase P, the chromatic number goes up, and I guess you wouldn't be able to increase it so that not somewhere in between, it wouldn't be concentrated on the 2 points just before it jumps.
Okay.
If you had 1-point concentration. So I think 2-point concentration is in general the best you can hope for. Right. Okay. Okay, now, so yeah. So we want to show, and it actually has, the theorem has actually a reasonably short proof, so I can kind of get through the main argument, maybe not every last detail, but I think I can get through the main argument in the remainder of the talk. Okay, so I should tell you who proved this. So there's a paper on Archive from last year where I had it up to n to the 1/4. And then quite recently, together with Oliver Reardon, we've been able to, to push this up all the way to n to the 1/2 minus epsilon. And if you compare this to the upper bound by Shamir and Spencer, or this slightly improved upper bound by Alon, you can see that the exponent up to this little epsilon, the exponent matches. And you could also here, you could write some function instead of epsilon that tends to 0 sufficiently slowly. Okay, so before I get into the details of the proof, let me try to convince you why this theorem should hold. So intuitively, why we should expect the chromatic number of G(n)1/2 to be not too concentrated. So for that, I have to talk about independent sets for a bit. An independent set is a vertex set without any edges between them. So in a coloring, by definition, every color class, all the vertices of one particular color are an independent set because you can't have any edges where the endpoints have the same color. So that's why independent sets are interesting when you study the chromatic number. Okay, and the independence number of a graph is the size of the largest independent vertex set. And we denote that by alpha. Okay, and so for our favorite random graph G(n)1/2, the independence number is basically known. So this is an old result from the 70s, I think, by Bollobás and Erdős. So you can show using the first and second moment method that the independence number of G in 1/2 is basically known exactly. It's this explicit expression that you don't have to remember, but you round it down to the nearest integer below it, and basically that gives you the independence number of G in 1/2. So there's this little slightly annoying little O1 term that you can't get rid of. So in some cases it might take one of two values, but most of the time it's actually 1 point concentrated. Okay, and we know even more about these large independent sets of G in 1/2. So if you count the number of maximum independent sets, number of independent alpha sets in G in 1/2, then because there are relatively few of them, you can show that they are roughly Poisson distributed. Now I have this mu here in the Poisson distribution. That's the expected number of alpha sets. And well, what is that? It turns out that you can write mu as some power of n. You can write it as n to the x. And this exponent actually depends on n. So yeah, I've drawn this picture here where you can see what the exponent does of the expected number of alpha sets. So for some n, the exponent is close to 0. So the expected number of maximum independent sets is close to 1. And then as you increase n, this exponent increases until the expected number of alpha sets is almost n to the 1. And then at that point, actually, the independence number jumps to the next integer because you've increased this expression alpha 0. So alpha becomes alpha plus 1, and then the exponent drops down to 0 again. So yeah, so this is what the exponent of the expected number of maximum independent sets does. And now the point of all this is, we know these alpha sets are Poisson distributed, and we know therefore that they vary by about n to the xn over 2, because that's just the variance of a Poisson, sorry, the standard deviation of a Poisson random variable. And it actually takes different values that are this far apart. Okay, so we know the number of independent alpha sets is not too concentrated. So in particular, if we pick some n that is somewhere here, where the expected number of alpha sets is kind of almost n, then the number of alpha sets varies by almost root of n. Okay, so what does all of this have to do with the chromatic number? Well, so I already mentioned earlier that the chromatic number is kind of closely related to the independence number. So as if you have a coloring, every color class is an independent set. Every color class is of size at most alpha. So if you have n vertices, you're going to need at least n over alpha colors, because every color class has size at most alpha. Now this is a lower bound that holds for every graph, but for random graph, this is actually kind of very close to the truth. So it's asymptotically correct for random graphs. And for G in 1/2, we know actually that the chromatic number is roughly n over alpha 0 minus some constant. So this is the formula that we had on the kind of the second slide of this talk, I think. Okay, and every color class has size at most alpha, so we know we can color G in 1/2 so that the average color class size here is only a constant away from the maximum any color class may possibly be. And even more, it's very plausible that the optimal coloring of G in 1/2, or an optimal coloring of G in 1/2, contains all or almost all independent alpha sets. And that's because, well, if you want to color G in 1/2 and you build up your coloring, and you get to choose your color class sizes, with a given total number of colors, then it turns out that the thing that works best, the thing that maximizes the expected number of colorings, should contain as many alpha sets as you possibly can. Yeah, so to maximize the expectation, you should try and get as many alpha sets as you can into your coloring. By the way, that's no longer true if you look at alpha minus 1 sets. So there, it's not always the best thing to take in as many alpha minus 1 sets as you can. But for alpha sets, it's true. And we know the number of available alpha sets, x alpha. We know for some n that wobbles by almost root n. So the total number of colors you end up with in the end, if you have to include all of those in your coloring, should also wobble at least by that much. So that makes it plausible that there are some n, at least, where the total number of colors you end up with kind of changes by almost root of n, depending on how many alpha sets you have available. So you might be able to maybe divide this by another log factor, because you can take some leftover vertices and distribute those onto smaller color classes. But still, if the number of available alpha sets goes up and down by root n, roughly so should the chromatic number. Okay, so that's kind of what I wanted to say about the reason why the proof works. Now, if you have this kind of intuition, yeah, that's the picture again. Yeah, so if you have this kind of intuition, let's see how we would make the proof work. So we start out by saying, okay, suppose we have some sort of sequence of intervals that contains the chromatic number of g and 1/2. And our aim is now to find at least one long interval for any given sequence of intervals that contains the chromatic number of g and 1/2. So note that we're only finding one particular n star that has a long interval. We're not showing anything for every n. So yeah, we're just finding one where it's not too concentrated. Okay, so a good candidate would be some n so that mu, the expected number of maximum independent sets, is close to n. So that the number of available alpha sets varies by almost root n. And we're going to find some n star that's close to this n, but it's actually not always going to be n. Okay, so how might you try to prove this? If you know about the variation in the number of alpha sets. So first attempt you might have, or first idea would be, might be, well, okay, we could look at different instances of g and 1/2, conditional on some number of alpha sets. So here we could condition g and 1/2 on having a alpha sets, where a is some typical number, say roughly the expected number of alpha sets. And then maybe we could introduce some extra alpha sets into g and 1/2. So we could condition g and 1/2 on having a plus r alpha sets, where r is the standard deviation of the number of alpha sets. So this is still a typical value of x alpha that it takes with a reasonable probability. And our hope would be kind of to show that as x alpha goes up, the chromatic number goes down accordingly. Or conversely, maybe if you have a coloring and you kill some of the alpha sets, r of them, then the chromatic number goes down. Now, I tried this kind of approach for a long time, and I could never make it work. And the reason I couldn't make it work was, well, there's no way to ensure that your optimal coloring uses these alpha sets. So it might be that you take out some alpha sets, but there's another coloring that doesn't use these alpha sets. Or you could give the graph some additional alpha sets, but still there isn't a better coloring than what you had before that uses these alpha sets. So yeah, I tried this for a long time. I couldn't make it work. So the trick that kind of does make this idea work is to compare GN1/2 with different available number of alpha sets, but not for the same n, but also for different n. Okay, so the picture I want at the end of the proof, or in the middle of the proof actually, is this. So I want to have a GN1/2, and I want to embed it into a slightly larger GN prime 1/2. So n prime is n plus r times alpha, and I want the difference to consist of these independent alpha sets. So it's not clear, of course, how I might get such a construction, but this is kind of the thing I want. So I'm not telling you yet what I then plan to do with this construction, but maybe it's plausible that this would be a useful thing to have to study the chromatic number. Okay, so I kind of want to have a GN1/2 embedded into a random graph that is similar to GN prime 1/2. I'm going to say in a minute what I mean by similar. And the construction I have is, well, I'm just going to plant R random alpha sets into GN prime 1/2. So I'm going to pick some random alpha sets and condition, so vertex sets of size alpha, and condition on these alpha sets being independent. And then I take every other edge independently with probability 1/2. And so the first step is I want to now show that if R is not too large, this construction I end up with is very similar still to a GN prime 1/2. Okay, so the key lemma here is the following. So I say I'm putting in R independent sets, but it's actually cleaner to study the effect of just putting in one. So we call this the planted model. So the planted model, we just construct it in the following way. We take n vertices, or n prime vertices. We pick one vertex set of size alpha, uniformly at random, and then we include all the other edges independently with probability 1/2. And in our special alpha set, we don't put in any edges. Okay, and now the key lemma is that the total variation distance between this planted model and the normal GN1/2 is of order 1/root mu, where mu is the expected number of alpha sets. So on the next slide, I'm actually going to define the total variation distance if you don't already know what that is. But what this means is that you can couple this planted random graph and the normal random graph so that they give the same results with probability at least 1 minus something of order 1/root mu. Okay, so that's the key lemma. And actually it has a proof that fits on one slide. So I'm going to put it on the next slide. Now, if you just believe me and don't want to follow through the proof, then please bear with me and you can start paying attention again after this slide. Okay, so how do you actually prove this? Well, it turns out we can actually work this out explicitly, basically. So we can work out what the total variation distance between these two random graph models is. So for a discrete random variables, by random variable, I now mean the random graph. The total variation distance can be defined like this. So you write 1/2 times the sum over all values the random variable can take. In this case, a value of the random variable is a graph on n vertices. So you write a sum over all graphs on n vertices. And then you subtract, or you look at the absolute difference between the probabilities that the first random graph model comes out as exactly this graph, this particular graph, and, well, the probability that the other random graph model comes out as exactly this graph. So that's just the definition of the total variation distance. Okay, and you can work out these probabilities explicitly. Okay, so the first probability, well, if you have one particular graph on n vertices, then, well, the first thing is the alpha set that we choose, the special one, has to come out as one of the given ones in G. So that has probability number of alpha sets in G over n over alpha. And then the remaining vertices have to come out as present or not present, well, in the right way. So that has probability exactly a half to the n choose 2 minus alpha choose 2. So all the edges outside this special alpha set. Okay, and the second probability, hopefully we all know what it is. That's just a half to the n choose 2. Okay, and now we just need to rearrange these terms nicely. So I want to pull out a half to the n choose 2 here. And I want to write mu, the expected number of alpha sets in the denominator. And then what I'm left here is just the number of alpha sets in G minus, again, mu, the expected number of alpha sets in G in 1/2. Okay, and now maybe you notice that these things here, what we have in the front, are the weights that graphs get in G in 1/2. So we have a sum here over all graphs on n vertices, and here we have the weight this graph has in the random graph G in 1/2. So this is simply an expectation. So this is the expected number of, the expectation of the absolute difference between x alpha and its mean divided by its mean. And now, as I said, x alpha is a random variable, is a Poisson random variable. So it varies by about root of n about its mean. So we end up here with something of order 1 over root mu. You actually don't need the Poisson approximation for this. So it's enough here that the variance of x alpha is of order mu. And that's kind of not hard to check by hand. Okay, so this is the proof of this key lemma. If you've stopped paying attention, you can maybe now start paying attention again. Now, okay, so why does this help us? Okay, we know if we plant one alpha set in the graph, the difference in the random graph models is of order 1 over root mu. And I hope that makes it plausible that if I plant little o of root mu of these sets, then the total variation distance after doing that and the normal G n prime 1/2 is little o 1. Right, and what does this mean? This means basically the outer random graph has the same distribution as G n prime 1/2. So we can couple these two random graphs so that they give the same result with probability 1 minus little o 1. So anything that holds in one of them with high probability also holds in the other one with high probability. So in particular, you may recall in the beginning we said, suppose we have some sequence of intervals that contains the chromatic number with high probability. So in particular, the outer random graph has a chromatic number in the typical interval for n prime. And well, the inner random graph is just a normal G n 1/2. So that has a chromatic number inside the typical interval for n, both of these with high probability. Okay, so that's good. But we also know something else about these random graphs. So this is why I wanted to have a construction like this. We also know that the chromatic number of the outer random graph is at most the chromatic number of the inner random graph plus r. And that's because if you have a coloring of the inner random graph and you add all of these independent sets as their own color classes, that gives you r additional colors and you've colored the whole graph. Okay, so the chromatic number of the whole thing is at most chromatic number of the inner thing plus r. Okay, and so with high probability, this guy is at least the lower end of the interval for n prime as n prime. And this one is at most the upper interval for n, the upper end of the interval for n, and now plus r, which is the lower end plus the length of the interval plus r. Okay, and now rearranging this term, we have a lower bound for the interval length. So yeah, so we have a lower bound for the interval length. It's Sn prime minus Sn minus r. And while this statement up here holds with high probability, because these things are random variables, here we only have functions of n and n prime. So this actually holds always. Okay, so we have a lower bound for the interval length, and that's nice. But what does this help us? Because we don't actually know anything about what Sn and Sn prime are. So this is kind of the second trick. So what we do now is we plug in the estimate that we have for the chromatic number from the very beginning of the talk. So you may recall we had some estimate for the chromatic number, which holds up to accuracy little o of n over log n squared. Now, if we just forget about this error term for a moment and just look at the estimate, so if you plug in what all of these things are, what n and n prime mean, it turns out that if you subtract the estimates from each other, you get something of size r plus order r over log n. And if we pick r so that it's just below root n, so that's possible if we pick n so that the expected number of alpha sets is just below n, then this here is also just below root n. So at least n over n to the 1/2 minus epsilon, say, for some fixed epsilon. And now if you plug this in up here for Sn prime and Sn, you can see r cancels, but we're left here with a term that is basically exactly what we want. It's r, the number of extra alpha sets we have available, okay, divided by a log factor, which kind of makes sense. Now, again, maybe now you're very happy that you have this lower bound for the interval length, until you remember about the error term. And then you look at the error term and you see, okay, it's actually much larger than this lower bound that we want to show. So it looks like this is completely useless. And now the third step, which I'm not going to get into now because it's a little bit boring, but you have to do kind of a final technical argument to make this work. So what makes this work in the end is to look at a sequence. You repeat this argument basically for a sequence of values, n prime, and prime, and so on. Yeah, you add this thing up and take averages basically. And you only plug in, if you take enough of these values, then in the end, the sum of these lower bounds actually beats the error term. So yeah, if you're really interested in this, you can check out the paper, or you can just believe me that by looking at a sequence of values, you can make this work and find some n star nearby where the lower bound that we wanted up here actually holds. So some n star close to n, so that the length of the interval there has to be at least n star to the 1/2 minus epsilon. Okay, so that's all I wanted to say about the proof. Okay, so let me finish up with some things that are still open. Okay, so you might have noticed in the proof that we only find some n star where the chromatic number is not too concentrated. And I guess we can, for every n, we can find some n star close to n where the chromatic number is not too concentrated, but for any particular n, we can't prove anything. So it would be very nice to have some sort of statement that holds for every n, or for every large enough n, say. Now, ultimately, of course, what we want is to find the correct concentration interval length. And I very much suspect that the exponent of the correct length depends on n. So like it does for the exponent of the concentration interval length for the number of alpha sets. So I think this gamma is some function of the exponent for the number of alpha sets. Right, another angle is, well, the upper bound that we have for the concentration interval length is root n over log n, and our lower bound now gives n to the 1/2 minus little o1, where little o1 is some function that tends to 0 relatively slowly. Now, how close together can we actually put these things? So as it currently stands, we can't get anything better than this, because this little o of one term is, so the bottleneck here is the accuracy of our estimate for the chromatic number that we plug in. So at the moment, this is the best you can get from this approach. If you wanted to improve this, you'd first need a better explicit estimate for the chromatic number. And this is a sort of preview. I'm not claiming this yet, but it looks like we might be able to push the lower bound to root n over log n to the 5. But that depends on a better explicit bound that I'm working on in a separate project with Kostas Panayiotou. Okay, so this might be on the horizon. Yeah, and finally, all of this was about gn1/2. I think it also works for all other constant p. But what about other ranges of p? So in particular, we know if p is small enough, there's 2-point concentration. So it would be interesting to see how far down this approach can be pushed. So in particular, is it true that maybe after this point, n to the -1/2, do we maybe have non-concentration sort of immediately after or not? Right, thank you. Those are all the open questions. Oh, and I've finished in plenty of time.
Thank you, Annika. It's a wonderful talk. Okay, so are there any questions? Should probably let me. For some reason, I don't see the button of unmuting everyone. Do you see it, Diana?
So so I can unmute everyone if that's what I should do. And also, can I ask a question, please?
Can I cut in front of Hamza?
I'll also ask the question, so if you don't mind.
So my question is, like conceptually, like why were these maximal independent sets so much more important than independent sets one vertex smaller?
Well, there are quite few of these maximum independent sets. So you essentially can put all of them in your coloring. So of size 1 smaller, more of them are available, and they actually intersect in vertices, so they are not disjoints. So you can't take all of those into your coloring. But with the alpha sets, you basically can have almost all of them in your coloring. But that's not the whole reason. It's also the case that for the alpha -1 sets, you don't want the optimal thing to maximize the expectation in the number of colorings is not to take in all the alpha -1 sets. And I don't know of any other reason than this is what comes out of the optimization problem.
Mm-hmm. Okay, thanks.
Next, I believe, is Alp. Alp, I think you can unmute yourself.
Hi. I was curious what your intuition is for the first problem you raised. Would you expect there to be?
Yes, I think it's true for every n. It's just that our proof doesn't give it for every n. It's because of the so if I go back to the last slide, because of this error term here, it doesn't work for one particular n. You have to put in this technical argument in the end, where you then find some n star close to n. But yeah, I would very much suspect that it's true for every n, that this is a lower bound.
Thank you.
Thank you.
I think next is Jan Balaz.
No, it's Matas.
Oh, I thought you raised your hand before. Okay.
Thank you. It's not a clever question, just catching up with you about when you say n star, you mean that your lower bound holds for some subsequence.
Yeah, you could, I find one n star, but of course I could also construct a sequence, an infinite sequence like that where the lower bound holds. Yeah.
And what is the lowest bound which holds for every n? What's the worst? Well,
I mean,
the best lower
nothing.
bound.
We know nothing for every n.
It is still 2 or something, right?
In principle, there could be one particular n where it's 1 point concentrated. As far as we know, I don't think it's true. But the proof doesn't give us anything, or I don't know of any other argument that would show that.
Okay.
Yeah.
Thank you.
Thank you.
Okay, any more questions? Ross has a question. He says, what about random regular?
I haven't tried doing it for random regular graphs, so I don't know. Maybe there's some easy way to do the same thing, but I haven't tried it.
Okay, I actually, Albas, another question, he says, does the proof work for any non-constant value of P?
Yes, so it works in exactly the same way if P is less than 1 minus 1 over E squared, which is about 0.86. And it gets a little bit annoying if P is bigger than 0.86, but it still works. So this little annoyance comes from the formula that we have for the chromatic number of G1/2, which changes its form for P past 0.86. But yeah, it works for every constant P, just in a slightly different way if P is more than 0.86.
Okay, Alp says he means when P tends to 0 very slowly.
Well, I would guess it works, but we don't have this formula for the chromatic number that we use for P tending to 0 slowly. So first you would have to extend this formula to that case, which I suspect is possible. Yeah. But I don't know for sure.
Okay, nice. Okay. Fiona, do you want to ask your question or do you want me to ask the question?
Oh, yeah, I can ask if you can hear me. Yeah, sorry. So you said at first it was a proof about n to the quarter instead of approximately n to the half. So maybe you can tell us a little bit about where the jump was, like where the improvement happened.
It happens in the coupling argument. So in this picture I drew earlier, do I want to go all the way back? It's not so far. Okay, so in this picture here, so the new kind of ingredient, or the main new ingredient, is that we only plant these R random alpha sets. So originally, the original argument planted all of the alpha sets. So this inner random graph also had some planted alpha sets. And then it only worked in the case when all the alpha sets are disjoint.
Cool.
And that only happens when we have less than root of n alpha sets. So then if you get close to root of n alpha sets, you have some alpha sets that intersect in one vertex, and I couldn't make the coupling argument work anymore. Yeah, and that gives n to the 1/4 non-concentration. So the main new thing is this new form of the coupling argument, which also is now shorter than it was before. So yeah, it became more, it worked for more and it's also now simpler.
Yes, thanks.
Okay, any more questions? Annika, do you mind if I ask, I reiterate the same question that Pelek had before? about the one concentration. I'm not sure I got that. Why is it that we can't expect to have 1 point concentration? Is it because of monotonicity and some lower bound?
Okay, so if you fix n and you have some p, and you increase the p slowly from 0 to 1, and suppose it was always 1 point concentrated, then as you increase p, first it's 1 point concentrated on one particular integer, and then at some point it would jump up to the next integer. But sort of by continuity, the probability is a continuous function in P, that you have chromatic number, whatever, K. So it can't jump up discontinuously from being close to 1 for K and then being close to 1 for K plus 1. Somewhere in between, if you pick the right P, it has to have weight, say 1/2 on K and K plus 1.
Okay, thank you.
Thanks.
Any more questions? Okay, if not, we will stop recording then. But before that, may I ask everyone to unmute themselves and give a round of applause to Annika for a wonderful talk.